So today what I want to talk about is how can we find some exact values for the trigonometric functions? And there's a few angles for which we actually do know exact values. If I think about going back to the unit circle, let me make a quick unit circle because I didn't think to actually do that before I started the camera. Okay, for an angle of 0, this is the point 0, 1, and so we can say that the cosine of 0 is equal to 1, the sine of 0 is equal to 0. If I look at this point up here, this is the point 1, 0. Well, this is a right angle, which is an angle of pi over 2, and we can say, therefore, that the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. If I look all the way over here, so half a circle around, that is going to be an angle of pi, and this point over here is minus 1, 0. So this tells me that the cosine of pi is minus 1, the sine of pi is 0, and then down here at the bottom, this point we know is going to be the point 0, -1. That is an angle of 3 pi over 2. So cosine 3 pi over 2 equals 0. Sine 3 pi over 2 equals minus 1. Okay, so these are 4 angles where we actually know the exact value here of our trig function. Sorry about that. Just adjusting something really quickly. Okay, so we want to know some more angles here. Now, unfortunately, it turns out to be impossible, as I've said before, to give a nice formula for these trig functions. And one of the reasons for that is because, well, like we said before, you can tell that this can't be a polynomial because polynomials can't be periodic. And these are periodic functions. If you don't remember what that means, make sure to go look in your book or go back and look at the video on that. But the brief version is that it means, well, cosine of x is actually equal to the cosine of x plus 2 pi. In fact, it's equal to the cosine of x plus 2 pi k. So basically, when you look at the graphs of these things, horizontally shifting them by a multiple of 2 pi doesn't change the graph. In other words, these functions keep on repeating themselves, and that's not something a polynomial can do. It's actually not even something a rational function can do. If you go back to the way rational functions behave, they eventually have to start asymptotically approaching a polynomial. So there is no formula for these in terms of polynomials or even rational functions. And you might think, well, what if we start throwing in things like radicals? Maybe we can take square roots and things. It still doesn't really work out because when you start taking square roots of polynomials and rational functions, yeah, they still can't repeat themselves, because if they started repeating themselves, then those polynomials or rational functions would repeat themselves. Okay, it's a long-winded way of basically saying there's no nice formula for these things in terms of arithmetic operations. And it turns out that because of this, we can't necessarily give exact values for these trig functions for any given number, for any given angle. But we can actually figure it out for some specific angles. And kind of the easiest way to think about this is going to be to think about it in terms of triangles. So we're going to work out some values for the trig functions by appealing to some special triangles where we can use the geometric properties of triangles to help us out. Now, remember, the trig functions, you can kind of think of them as either being defined in terms of the unit circle, or you can think about them in terms of their triangle behavior. And so in the previous video, we looked at how do these trig functions relate to the dimensions of triangles. So again, if you don't remember that, make sure to go back, review that material, and then come back here and keep watching this video. One of the nice things actually about this whole online lecturing business is that you guys can switch back and forth. You can kind of say, oh, I don't remember this. Let me go quickly look at that again, and then I'll come back to here. Anyway, so I'm going to start with the following kind of triangle. Suppose that I have a right triangle, and I want to say that these two sides have the same length. In fact, we're just going to set their length at 1, because why not? I'm going to pick it to be 1. I could pick it to be anything I wanted to, but let's make things easier on ourselves, and let's just pick it to be 1. It turns out not to really matter. Okay, well, one of the nice things that we know from the geometry of triangles is that means that these two angles are actually the same. So these both have to be the same angle because these two sides are the same. And this is something that you probably would have seen in, say, a high school geometry course. So what this means for us is, well, first of all, this is a right triangle, and it means that we can compute what is this hypotenuse. Well, the hypotenuse, let's call that c. We get c squared equals 1 squared plus 1 squared. That means that c is going to be equal to the square root of 2. So I'm actually just going to write in here that that is the square root of 2 here. Okay, now, here's the thing. We know that the cosine and the sine, even though they're defined in terms of the unit circle, you can actually compute them by looking at the ratios of these different sides. So, what would be this cosine and what would be this sine? And perhaps even before we answer that, we should ask the question, what actually is this theta? Well, to figure out what this theta is, we remember that all of the angles in a triangle have to add up to pi if they're in radians, or 180 degrees if we're in degrees. So theta plus this right angle of pi over 2 has to equal pi. Okay, well, go through this for a moment. It's not too difficult to figure out what theta has to be. It has to come out to be theta equals pi over 4. In degrees, I will leave it to you guys to work out how you get it in degrees, but the answer is it would be 45 degrees. Now, what would the cosine and the sine of these angles be? So we're looking at the cosine of pi over 4 and the sine of pi over 4. Well, what is cosine? It is adjacent over hypotenuse. So if I think of this as my angle, this down here, and this side is then the adjacent, I get that the cosine is 1 over the square root of 2, which if I multiply on the top and bottom by square root of 2, that becomes square root of 2 divided by 2. What about the sine of pi over 4? Well, for the sine, remember this angle down here is pi over 4. This is the opposite side. This is the hypotenuse. This is also going to be 1 over the square root of 2, which comes out to be square root of 2 over 2. I've written these down in terms of radians, but of course we could also write it down in terms of degrees. So we could say cosine of 45 degrees is square root of 2 over 2, and we could say the sine of 45 degrees is square root of 2 over 2. Whoops, that is not really a 2. There we go. That's a much better looking 2. So you see how we were able to start with, hey, here's a triangle whose dimensions we know. And from that, we can compute the sine and the cosine. The problem is that for a general angle, we may not know a priori what the dimensions of the triangle are. So in this case, we were kind of lucky in some sense. All right, now make sure that you guys understand this, but I'm going to go on to working out the next type of triangle here. Okay, so the next kind of triangle that we're going to look at here is, what if I take a triangle, and I want to make this one a little bit bigger because we're going to do some additional stuff to it. What if I take a triangle where all three angles are the same, and that means that all three sides are the same. So remember that in geometry, we indicate that all three sides are the same by putting little tick marks, and we put the same number of tick marks on all the ones that are of the same length. So these are all supposed to be of the same length. And, well, the first thing that you're probably going to think about here is, what does this angle theta have to be in this case? Well, if I work this out in radians, I get that theta plus theta plus theta has to equal pi. That means that theta is equal to pi over 3. If I wanted to do this in degrees, that would come out to be 60 degrees. Now, the thing is that this is not a right triangle. So you might be wondering, why on earth would I bother with this thing if it's not a right triangle? Well, here's the thing that I can do that is going to give me a right triangle that I can work with. I'm going to start at the top here, and I'm going to drop a perpendicular line down to the bottom. Now, I claim that this perpendicular line cuts the base of this big triangle in half exactly. I'm not going to prove that. That's something that you would prove in a geometry course. It's not too difficult to prove that, well, because these two lines have the same length, this perpendicular is going to cut this line in half. In fact, if you remember back to your geometry courses, this is actually how you would bisect a line. Bisecting a line meaning how you would take some line and chop it in half directly in the middle. So for our purposes, all you really need to know is that, yeah, this really does cut this thing in half. So these two sides have exactly the same length. The other thing to notice here is that this angle, the one that I've indicated with the double angle arc thing, is going to therefore be exactly half of theta. So this is actually theta over 2. Now what that means is that this angle down here is pi over 3. This theta over 2 is therefore pi over 6. And I do apologize, I probably should have made this triangle even bigger. Like I said, I wanted this one to be somewhat big because I need to do a bunch of stuff with it. But hopefully you can see what this all refers to. Well, now I have a right triangle to work with here. And because I have a right triangle to work with, I can now appeal to what we know about the relationship between trig functions and the dimensions of a right triangle. So let's get to work on that. Let's start off with saying, let's suppose that I make this hypotenuse a length of 2. Okay, what happens next? Well, if this side is a length of 2, then all 3 sides of the big triangle are a length of 2. Now, let me ask you a question, and think about this for a second, although you'll probably maybe get the answer really quickly. If this is a length of 2, what happens if I take half of that length? Okay, well, half of 2 is just 1. So this side here has a length of 1. In other words, what I've actually got here, and let me draw this triangle on the left. Let me draw a new copy of it that is, oh my God, that's not even a line. Let me draw a new copy of it that is maybe less cluttered. This angle down here is pi over 3. This angle up here is pi over 6. And this hypotenuse is 2, and the bottom here is 1. So this triangle is really just this triangle. I just wanted to draw it with a little less clutter here to make things easier to see. What is the height of this triangle? Well, if I call this side b, the Pythagorean theorem tells me that 2 squared is equal to 1 squared plus b squared. That gives me 3 equals b squared, or square root of 3 is equal to b. But look at this thing now. Now, I have a triangle. I know the lengths of all 3 sides. I know what these angles are. I can now use the fact that the cosine is adjacent over hypotenuse, and the sine is opposite over hypotenuse, and I can write down the sine and the cosine. So, the cosine I'm going to erase this, so make sure to take notes on this really quick. I just want more room to write down here. The cosine of pi over 3 is equal to the adjacent side here of 1 divided by the hypotenuse. So 1 over 2. And notice that this is the same thing as the cosine of 60 degrees. If we wanted to work these problems in degrees, we could do it that way. The sine of pi over 3 is going to be the opposite side divided by the hypotenuse, which is square root 3 over 2. And this is, of course, the sine of 60 degrees if you want to write down the trig functions in terms of degrees. But we can get more than just this pi over 3 angle out of this triangle. We can actually get the pi over 6 as well, because that's an angle on here too. Let me erase this original triangle, and we'll start writing that down. Whoops, I have accidentally erased my cosine pi over 3 as well. Okay, so cosine of pi over 6 and sine pi over 6. Now, what I would like you guys to do is take a minute here and pause this and see if you can work out what these two values should come out to be on your own. Try to imitate what I did down here. Okay, so we're back. Hopefully you guys were able to get an answer. If not, let me show you how I would think about this. And even if you did get an answer, let's double check, make sure that everybody's on the same page here and got the same thing. Well, the cosine of pi over 6 is adjacent over hypotenuse, but this time the adjacent side is this b equals the square root of 3 thing. So the cosine of pi over 6 is square root 3 divided by 2. The sine of pi over 6 is going to be opposite over hypotenuse. Well, the opposite side this time has a length of 1. So this is going to be 1 over 2. And of course, if I wanted to write this in degrees, I could say this is actually the cosine of 30 degrees. This is actually the sine of 30 degrees. So we've actually been able to find the exact values for sine and cosine at several different points. Several different angles, that is to say. Now, this is a good place to take a little break if you want to, and then we're going to talk about the labels on the unit circle, the angles on the unit circle that are kind of key to memorize and remember. All right, so let's go ahead and make a big unit circle, and we're going to start labeling some angles on it. This is going to have to be as big as I can make it because we're going to put a lot of information on this thing. The good news is that even though there is a lot of information on this, memorizing it turns out to be, I won't say easy or straightforward, but there's a lot of good tricks. And these really are good tricks. You know that I do not like memorizing things, but these are some really good tricks for memorizing all the information that's contained on this circle. One thing I want to remind you guys of that maybe you remember from the basic Cartesian plane stuff is the plane is broken up by the x and the y axis into 4 different pieces. And because each of these pieces is sort of like 1/4 of the plane, we call these quadrants. And this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. Now, that's not something that's super important for this. Let me make this circle slightly more circular here. That's driving me nuts. This is not super important, but it's good to have that terminology in mind. I just want to remind you guys of it so that if I start saying quadrant 2, you know what I'm talking about. Okay, so the first thing that we can do is we're going to label sort of the 4 cardinal direction points here. We know what these points are going to be. This is going to be an angle of 0, and the coordinates of this point are 1, 0. We know that this is an angle of pi over 2, and it has coordinates of 0, 1. This is an angle of pi with coordinates -1, 0, and then we get 3 pi over 2 with coordinates of 0, minus 1. All right, now, we just found several other angles. We found the angles pi over 6. Now, pi over 6 is 1/3 of the way through the first quadrant here, because if you put 3 of these together, you have to get pi over 2. We also found pi over 4. Pi over 4 is halfway through the first quadrant. Sorry, that was not really halfway through the first quadrant. Maybe that looks a little bit better. And then we have pi over 6, which should be about 2/3 of the way through the quadrant. So this is going to be our pi over 6 angle. Well, the cosine of pi over 6, we said that one is going to be square root 3 over 2, and the sine is 1 over 2. So the x and y coordinates on the unit circle at the terminal point are the cosine and the sine, which means that I can label this point as square root 3 over 2 and 1/2. For pi over 4, I can do the same thing. We said the cosine of pi over 4 is square root 2 over 2, and the sine of pi over 4 is square root 2 over 2. Okay, that means that the x-coordinate is the cosine, and the y-coordinate is the sine. Well, in this case, they both happen to be the same thing, so they both just become square root 2 over 2. Now, why did I write pi over 6 here? That is clearly incorrect. That should be pi over 3. My apologies. If we look at this pi over 3 angle, take a minute here and see if you can figure out what should I put as the coordinates of this terminal point. And as a hint, remember, this should be the cosine in the x-coordinate and the sine in the y-coordinate for an angle of pi over 3. Were you able to think of it? Well, the cosine of pi over 3 is 1/2, and the sine of pi over 3 is square root 3 over 2. Okay, so we have now labeled all of the angles that we know that fall in quadrant 1, starting at an angle of 0 and going up to an angle of pi over 2. Now, I want to say something about memorizing these angles. The first thing you want to notice is you do kind of just have to memorize that the angles go 0, pi over 6, pi over 4, pi over 3, pi over 2. But that's not too bad, because you start at 0, and then you have pi over 6, which is 1/3 of the way through, and then everything else is just literally pi over 4, pi over 3, pi over 2. So the denominators just kind of start counting down. Now, there is a nice pattern here that is going on. So if you notice, another way of writing this would be the coordinate is the square root of 4 over 2 and the square root of 0 over 2. And this coordinate is really the same thing as the square root of 0 over 2 and the square root of 4 over 2. Now, why would I want to write it that way? Well, it's because it makes a really nice pattern in the x and y coordinates of these terminal points. Look what happens to the y coordinates. Everything is actually, because I can put a square root here over the 1, since square root of 1 is still 1. And look what happens to the y coordinates. We have square root 0. Well, why did I put square root 0 over 0? I meant square root 0 over 2. Sorry, I don't know why I'm having so many problems with writing things down today. Apparently, I've lost my mind overnight or something. Anyway, square root of 0 over 2. Then we have square root of 1 over 2. Then square root 2 over 2. Then square root 3 over 2. And then square root 4 over 2. So the y coordinates are just square root of something over 2, and they go 0, 1, 2, 3, 4. And that's it. That is a really nice pattern that can help you remember the y coordinates of these terminal points. But remember, also, what is the y coordinate? It's the sine of the angle. Now, what about the x coordinates? The x coordinates are going to give us the cosines. And they follow exactly the same pattern except in reverse. So this one starts at 4 and goes 4, 3, 2, 1, 0, but it's still just the square root of the number divided by 2. So it just counts down from 4. Sine counts up from 0, cosine counts down from 4, but they all follow this square root of something over 2 kind of pattern. So that's a really useful way of memorizing these cosines and sines for the angles in the first quadrant. Now, what about the rest of these angles? Well, it turns out that there is a very nice trick for dealing with the rest of these angles. And that is, to get the values in any other quadrant, we just have to think about how could we reflect the first quadrant into that other quadrant. So let me show you what happens with quadrant 2, and then we're going to see how that really helps us out with quadrants 3 and 4. If I were to reflect the first quadrant into the second quadrant, this angle here that I'm pointing at, hopefully you guys can tell which one it is, this would be pi over 3 less than pi. Well, that comes out to be 2 pi over 3. And what are the x and y coordinates? Well, when I take this reflection, it just takes the x coordinate and flips the sign, and it leaves the y coordinate the same. Okay, what happens when I flip the pi over 4 angle? Well, now I'm pi over 4 less than pi, so that gets me to an angle of 3 pi over 4, and the x coordinate becomes negative square root 2 over 2, the y coordinate remains square root 2 over 2. What about when I flip the pi over 6? Well, you're probably going to see the pattern here. This angle, going all the way over to here, is pi minus pi over 6. That's going to become 5 pi over 6. And what happens to these coordinates? They just become minus radical 3 over 2, comma, radical 1 over 2. Okay, so here's the thing. If you remember the first quadrant, you don't even really have to memorize the second quadrant, because the second quadrant, you really get it from this first quadrant by just flipping all of the cosines to being negative. In other words, you take all of these x coordinates, you make them negative, that gives you your second quadrant. Now, we can use these top two quadrants, reflect them down to the bottom, and that's going to give us quadrants 3 and quadrants 4. So let's see how that works. First of all, if you're as bad at drawing straight lines as I am, that is really the challenging part of this for me, is making all these lines in a way that doesn't look completely ridiculous. So give me a moment here as I attempt to do that. Okay, so if we keep on going here, this angle here is going to be pi plus an additional pi over 6. So that becomes 7 pi over 6. Then we get pi plus an additional pi over 4. So that should be 5 pi over 4. And then we're going to get pi plus pi over 3. So that should be 4 pi over 3. Then we're up to 3 pi over 2. And then as we keep on going here, it's maybe easier to go the other way. So if we started at 2 pi and subtracted pi over 6, then this would become an angle of 11 pi over 6. 2 pi minus pi over 4 would become 7 pi over 4. And 2 pi minus pi over 3 would be 5 pi over 3. Okay, we have the angles now. And here's a brief challenge for you guys to figure out. See if you can fill in the x and y coordinates of all of these terminal points on your own. Now, this is going to be something that once you figure out the trick, it's still going to take you a minute to do this. So don't rush this. Take a minute and think about it and see what you can figure out. All right, hopefully you guys were able to figure this out, but the basic idea is I'm going to take the same idea as I did to get quadrant 2. I'm going to take this same let's do a reflection business, and I'm going to start reflecting into quadrant 3 and quadrant 4. Maybe I'll start with quadrant 4, actually, and we'll go around this way. When I vertically flip, the x-coordinate remains the same, but the y-coordinate becomes negative. So this becomes radical 3 over 2, comma, minus radical 1 over 2. Which, remember, that's really just negative 1/2, but I'm leaving the radical because it helps me memorize this pattern. Okay, flip this point. Square root 2 over 2, comma, negative square root 2 over 2. And flipping this point is going to give me square root of 1 over 2, comma, negative square root 3 over 2. Now, if you weren't able to figure this out at all, take a minute and think now that I've shown you how to do quadrant 4, think about how could I get quadrant 3? If you already finished this, then, well, you already finished it, so nothing more to really think about here. Okay, there's actually 2 ways at this point that I can fill in quadrant 3. I could start by flipping quadrant 2 vertically, or I could flip quadrant 4 horizontally. Either way, I'm going to get the same thing, which is good. We like to have consistency in mathematics. And I'm going to end up with, this angle is going to have a terminal point with coordinates negative square root 3 over 2, comma, negative square root 1 over 2. Then we're going to have negative radical 2 over 2, comma, negative radical 2 over 2. And then we're going to have negative radical 1 over 2, comma, negative radical 3 over 2. Okay. I just realized that you can't quite see the bottom here. I think I knocked into the camera at one point. I apologize for that. Fortunately, you just were missing the 3 pi over 2, 0, comma, negative 1 here. So hopefully that wasn't too confusing for you. As you can see, I really needed the entire board to write this down. But as complicated and as horrible as this thing looks, it is not too bad. If you remember that everything follows from this first quadrant, that's the first important thing. And the second important thing is, well, the patterns here. So remember, everything has the form square root of something divided by 2. And what are those somethings? Well, the y-coordinates start at 0, which makes sense because the y-coordinate is 0 down here. And they count upwards. So we go 0, 1, 2, 3, 4 inside the square root. The x-coordinates are 0 up here. That's kind of clear because, the x-coordinate on the y-axis is 0. So the x-coordinates start at 0, and they count 0, 1, 2, 3, 4 going this way. And again, if you remember this first quadrant, you will get the other quadrants. So that is a very important thing to keep in mind when you're memorizing this. All right, now, my drawing, not very pretty. Your book has a much prettier example of this kind of thing, or, they have the actual whole unit circle with all of these angles filled in your book that you can use. But it's a really good idea to be able to reconstruct this thing from memory. It's the kind of thing that will help you out a lot whenever you're working with trig function type stuff. All right, we're going to end there for now. Next time, we'll take a quick, brief look at what do you do when you are working with cosines and sines of triangles that actually have some of these angles in them, and what can we say about that sort of thing. So in the meantime, I hope everything is going well with you guys, and please do feel free to send me any questions that you have. We can also arrange to have meetups on Blackboard Collaborate outside of my regular office hours if those office hours don't work for you guys. So I will talk to you guys soon.